Hello again. I wanted to just expand a little bit with some examples on our rational exponents. So I'd like to show a few examples using the idea of rational exponents and how it relates to these root problems. So let's deal with the first one. And we're going to use that rational exponents. Remember, the first one, the square root of 2, this is 2 to the first power. And square roots have a 2 as their index, although that is not typically written. However, using the idea of rational exponents, that tells me that I can call this 2 to the 1/2 power times 2 to the 1/3 power. And again, here's the 1 there. The numerator of the fraction is the power of the number on the inside. Okay, the numerator of the fraction is the power of the number on the inside. All right, well, using the rules of exponents, I have the same base here, so I can add those powers together when I'm multiplying two exponential expressions. So this gives me 2 to the 1/2 plus 1/3 power, which is 2 to the, I need a common denominator here. Multiply that by 3 times 3, multiply this by 2 times 2. Don't forget that business. Okay, so this is 3/6 plus 2/6 equals 2 to the 5/6 power. And I could, if I wanted, turn this back into a root. So let me just draw my root symbol. 2 to the 5th power on the inside, the index is 6. And there we go. For the next one, we're going to play the same game. Turn this guy on the inside into a rational exponent and then deal with the power on the outside. So the first thing this gives me is 5 to the 3/4 power cubed on the outside. Now I'm going to distribute the power to the powers. So I get 5 to the 9/4 power, which equals, now I'll turn this back into a root, 5 to the 9th with a 4 on the outside. Now, 5 to the 9th is it's going to be some large number, so I'm just going to leave it as 5 to the 9th with the understanding that we all know how to evaluate that power if necessary. Okay, same business for the third example. Remember that if the power is not showing, I could put a 1 here and a 1 here, then we can use that. Or let's actually take a second look at this one before we continue. Let me just recopy this as the 4th root of 3, and maybe I can explain myself here in a minute, hopefully. I'm noticing that 27 is actually a power of 3. 3 to the something is 27, and it turns out it's 3 to the 3rd power. And we'll see here in a second why that's convenient. So again, this guy has a first power on the inside, so I'm going to write this as 3 to the 1/4 power times 3 to the 3/4 power. And here's why changing that into something having a power of 3 was convenient. Now when I'm multiplying these two guys, they have the same base. Okay, and since they have the same base, I can add the exponents, just like we were doing before. So this is 3 to the 1/4 power plus 3/4 power, which gives me 3 to the 4/4 power. The 4/4, wow, okay. Which is 3 to the 1st power, which is just 3 in the end. That's simplified nicely. It looked kind of ugly in the beginning, came out to a nice whole number there in the end. Now, in general, let's just take a look at this idea and produce maybe a rule using the rational exponents. So again, I'm going to say this is a to the 1st power and b to the 1st power, and call the first one a to the 1/n times b to the 1/n power. Now, this is interesting. I can't actually add those powers together because these bases are potentially different. What I can do, however, is I can say, well, this is the same as ab to the 1/n power. I actually factor that out. Remember, if I can distribute it, then I can factor it also. And what's the significance of this? Well, let me rewrite it in the root form. This means that what I have on the inside is ab, and on the outside to the nth power. Okay. So it simply means that if you have a couple roots like this, you can, if they have the same index, you can combine them and do the product of these two guys with the index on the outside. So that just gives you one more rule. So thank you for watching these exponent videos. It's been my pleasure for certain.